Alright, so if we're looking at an arithmetic sequence, right, an arithmetic sequence can be expressed using a general term. Tn is equal to a plus n minus 1 d. A here is the first term, okay, and we can call the first term t1. N here is the term number. D here is the common difference. For arithmetic sequences, we know that the common difference is constant, and d is equal to tn plus 1 minus tn, where tn plus 1 is the subsequent or the next term, and tn is the previous term. Oops. Okay, now tn here is the general term, and we can use this equation of an arithmetic sequence to determine a particular term if we know the term number. So these are what we call discrete functions, because the term itself is a function of the term number. Okay. So let's take a look at an example. If we had a sequence that looks like this, okay, you want to ask yourself, is this, first of all, an arithmetic sequence? Because we can only apply this equation if we have an arithmetic sequence. So what I'm going to do here is I'm going to do the common difference test. So d here is equal to tn plus 1 minus tn. And the common difference should be constant for all of the terms in the sequence, right? So this is term 1, this is term 2, term 3, and term 4. And in this case, the common difference here is 7 minus 2. If I test out term 2 minus term 1, so in this case it's 5. If I test out term 3 minus term 2, this is going to give me 12 minus 7. So you can actually notice that all of the common differences here are 5. And because all the common differences here are 5, we know this is an arithmetic sequence, so therefore we can use this equation, right? So now what we can do here is we need to write down our first term, a value. So for your arithmetic sequence, what you want to do is you want to fill in the gaps for a and d. Okay, and you can figure that out by looking at the particular sequence. And in this case, a here is 2, d here is 5, and if you plug this in, the general term here is tn is equal to 2 plus n minus 1 times 5, and what you want to do is simplify this. So I'm going to expand this guy out. So tn here is equal to 2 plus 5n minus 5. Tn is equal to 5n minus 3. So this is your general term. You can actually use this to determine any term number on this sequence. Like for instance, if we want to figure out the 100th term, we just plug this into the general term. We get 5 times 100 minus 3, which is 500 minus 3, which is 497. So it's really useful to determine any kind of term. So this is how we can use a discrete function. Okay, let's determine the number of terms in the following sequence: 9, 42, 75, it goes all the way to 4068. So first we want to do is we want to test to see if it's an arithmetic sequence. So an arithmetic sequence has a common difference d, which can be determined by taking the subsequent term tn plus 1 minus the present term tn. Okay, so what I'm going to do here is I'm going to test the subsequent term. So if I let n equal 1, so you get t1 plus 1 minus t1. This is t2 minus t1, right? So t2 is the subsequent term of t1. If I test these values, we get 42 minus 9, which is 33. I'm going to do the similar test with t3, its subsequent term to t2. We get 75 minus 42, which is also 33. So this tells us that d is constant. So if d is constant, we have a common difference that is present, and as a result, this is therefore an arithmetic sequence. So this is a way we can verify that this is truly an arithmetic sequence. So this is the template, the general term of an arithmetic sequence. We can notice that a here is our first term, so a is t1, which is equal to 9. Our common difference we calculated was 33. So if I plug that into this equation, tn is equal to 9 plus n minus 1 times 33, and I'm going to expand this guy out. And if I do that, Tn is equal to 9 plus 33n minus 33. And then what I want to do is clean up the expression here, so by collecting like terms, right? So you get 33n, 9 minus 33 is negative 24, and this is our general term. Now, using our general term, I want to figure out the term number of the 4068 term number, okay? So in this case, Tn is equal to 4068, and in this case, if we want to solve for n, 33n minus 24 is equal to 4068. So 33n is equal to 4068 plus 24. So this is going to give us basically 12904, so 4092, right? And now what we want to do is we want to solve for n, so I'm going to divide by 33 to both sides. And when you divide by 33, n was equal to 124. Okay, so this in fact is the 124th term of the sequence. Alright, for the following sequence, negative 49, negative 40, and negative 31, determine the general term, the 27th term, and if the value 90 exists in the sequence. Okay, so let's start with determining what type of sequence this is. So let's test to see if there is an arithmetic sequence. To test to see if it's an arithmetic sequence, I'm going to find my common difference d, which is the subsequent term tn plus 1 minus tn. Now in this case, the subsequent term of term 1 is term 2, so t2 minus t1 is negative 40 minus negative 49, which is negative 40 plus 49, which is 9. Okay, so the common difference between the first two terms is 9. Well, the difference between the first two terms is 9. We don't know if it is truly a common difference until it's constant. Let's test to see if the difference is constant between term 3 and term 2. So we get negative 31 minus negative 40, which is negative 31 plus 40, which is 9. Okay, so in this case, the common difference between all of these terms are the same. So this is truly an arithmetic sequence, right? So then we can use the general term Tn is equal to a plus n minus 1 times d. And if I wanted to find my general term, as according to part A, Tn is equal to a is our first term, so a is negative 49. So we get negative 49 plus n minus 1 d here is 9, right? And then what we do here is we expand this value, so we get 9n minus 9, and you want to collect all the like terms, so you get 9n minus 49 minus 9, which is negative 58. Okay, so this is your general term. Part B is asking us to find the 27th term, so all I have to do here is plug n is equal to 27 into my general term, and this is going to give me 185. And then for part C, we want to see if the value 90 exists on the sequence. Well, we know that if n belongs to the set of all natural numbers, then the term 90 will exist on the sequence. So we need to solve for a term number. Now I'm going to let Tn equal 90. And then what I want to do here is I'm going to equate this to my general term, so 9n minus 58. And therefore 9n is equal to 90 plus 58. 9n is equal to 90 plus 58 is going to give us 148. So if you divide by 9, right, just going to do it there. You divide by 9, n is equal to 16.4, and just the 4 would repeat. So this, therefore, 90 does not exist on the sequence. Okay, so because it's not a natural number, it's not a whole number, then, and it's not a positive whole number, it won't exist on this sequence. Alright, let's determine the 100th term of the arithmetic sequence with the 7th term T7 is equal to 465, and the 13th term T13 is equal to 219, right? So in this case, because in the arithmetic sequence, we can apply this general formula. Tn is equal to a plus n minus 1 times d, right? We know that T7 is equal to a plus, now this n here, the term number here is 7, so we get 7 minus 1 d is equal to 465. Okay, we don't have information regarding the a and the d value, but we just know for the time being the term number. Okay, so if you did want to simplify this, t7 is equal to a plus 6d is equal to 465. Okay, now we also know that t13 here is 219, and if you plug this into the general equation, you get a plus 13 minus 1d is equal to 219. If I simplify this out, you get a plus 12d is equal to 219. Now you can notice here that you have a series of two equations. One of your equations, a plus 6d is equal to 465. The second equation here is a plus 12d is equal to 219. Okay. Now, using the system of equations, we can actually solve for a and d. Right? So this is where you'd have to use substitution or elimination. The easiest way to do this is I'm going to do elimination, and I'm going to subtract. I'll do equation 2 minus equation 1. So if I do equation 2 minus equation 1, a minus a is 0, 12d minus 6d is 6d, which is equal to 219 minus 465. Okay, so 6d is equal to negative 246. And if you want to solve for d, I'm going to divide by 6 and then repeat the same thing to the other side. D here is equal to negative 41. Okay, so the common difference, you're adding negative 41 to the previous term to get to the subsequent term. Now, in this case, if your common difference is negative 41, what we want to do is solve for our a value. So you can actually substitute that into either equation 1 or equation 2. I'm just going to sub this into equation 1. So a plus 6d is equal to 465. A plus 6 times negative 41 is equal to 465. A is equal to 465 minus 6 times negative 41. And that's going to give us positive 711. Okay, so in this case, our general term here should look like Tn is equal to 711 plus n minus 1 times negative 41. Now I'm going to simplify this out. Minus 41, 41n plus 41, if I expand it out this way. And if I collect these terms, we get negative 41n. 41 plus 711 is going to give us plus 752. Okay. Now we're not done yet because we need to determine the 100th term, right? So it's a pretty long question. So we're going to do t of 100 is equal to negative 41 times 100 plus 752, right? And this is basically negative 4100 plus 752. And in this case, this is going to give us negative 3,348. Okay, so the 100th term, right? So therefore, T100 is equal to negative 3,348. So it's a little bit more complex of a variation of. All right, for the following sequence, 6, 12, 24, all the way to 1536, determine the general term, T12, and the number of terms present. Okay, so if we're looking at this, we want to notice, we want to first test to see if this is an arithmetic or a geometric sequence. If I look at the common difference, if I do T2 minus T1 here, I get 12 minus 6, and this is going to give us 6, right? And in this case, let me just change colors here. Let's use per orange. And if I test T3 and T2, I'll get 24 minus 12. And you can notice here that there is no common difference that's present, right? So there's no common difference. So because of the fact that there is no common difference, we know that this is not an arithmetic sequence. So now we need to test to see if it's geometric. So I'm going to look at the common ratio, which is defined as the subsequent term over the previous term. And in this case, I'm going to do this for T2 and T1, and you get 12 divided by 6, which is 2. And I'm also going to test T3 and T2, which will give us 24 divided by 12, which is 2. So if you actually divide the subsequent term with the current term or the previous term, you're actually going to see a common ratio existing. So if there is a common ratio that exists, then this is a geometric sequence. And we can model geometric sequences using a general term Tn is equal to a, r, n minus 1. And in this case, a is the first term, r is the common ratio, and n here is the term number. And Tn is a particular term, so it's a general term. Okay, so now if I wanted to find the equation of the general term here, Tn is equal to a here, which is basically the first term, right? So a here is 6, right? So 6, r here, we said that the common ratio is 2, right? So a is 6, r is 2. So we're going to do 2n minus 1, right? And you can leave your answer like this. Now in part B, they're asking us to find the 12th term, so we're doing t of 12. We plug in 12 for n, so we get 6 times 2 to the power 12 minus 1, which is 6 times 2 to the power 11. And you can leave your answer like that because this is a very large number. Now for part C, we want to figure out the number of terms present. You know what, I'm going to move this over here to make some space. So for part C, we know that the last term, Tn, is equal to 1,536, right? And you want to solve for n. So we know that the general term can also be expressed as 6 times 2 to the power n minus 1. I'm going to equate these two. So you have 6 times 2 to the power n minus 1 is equal to 1,536. And in this case, if I divide this by 6 to both sides to cancel it out, 2 to the power n minus 1 is equal to 256. Now 256, if you wanted to guess and check, you can actually determine that this is a power of 2, right? And specifically, this is a power, it's 2 to the power 8. Okay. Now, if you didn't want to guess and check, you can also use logs, specifically the power of logs. So what you can do here is you can do the log of the left side, and if you take the log of an exponent, you can actually move the power downwards and write it as a multiplication question. I'm going to do the same thing to the other side, so log of 256, right? And now you can rewrite this expression as n minus 1 times log 2 is equal to log 256. And your calculator, if you wanted to solve for n, because it's a multiplication statement, I'm going to divide by log 2. And whatever I do to this side, I'm going to repeat to the other side. Cancels out. N minus 1 is equal to, and if you punch this in your calculator, you will get 8, right? So n minus 1 is equal to 8. And then what you want to do, if you want to solve for n, I'm going to move the 1 to the other side, so n is equal to 9, right? So therefore, there is going to be 9 terms in the sequence. Alright, the 5th term of a geometric sequence is 45, and the 8th term is 360. Determine the 20th term. So because we know that this is a geometric sequence, then it follows that our general term Tn is equal to a, r, n minus 1. And in that case, a and r are missing values that we need to determine. So a is your first term, and r is your common ratio. We do know that the 5th term, T5, is equal to 45, and we know that the 8th term is equal to 360. Now if I plug this into our general term, T of 5 is equal to AR 5 minus 1 is equal to 45, right? And if you simplify this, is A times R to the power 4 is equal to 45. Okay, so this is the 5th term. I do the same thing for the 8th term. So the 8th term here is basically AR 8 minus 1, which is equal to 360. So the 8th term here is AR to the power 7 is equal to 360. Now what you want to do next is you have two equations called this the first equation, A times R to the power 4 is equal to 45. And equation 2, we have A times R to the power 7 is equal to 360. If you want to solve for A and R, what you could do is you could cancel out the A by dividing equation 2 by equation 1. So if I divide equation 2 by equation 1, we have AR to the power 7 is equal to 360 divided by AR to the power 4. I'm going to do the same thing for the right side. 360 divided by 45. A divided by A is 1. r to the power 7 divided by r to the power 4 is r to the power 3. We're using basically the exponent rule when it comes to dividing the same bases. So r cubed is equal to 360 divided by 45 is 8. And because r cubed is equal to 8, if we do the cube root of both sides, r is equal to 2. Okay, so now that we have r, you can substitute this into either equation 1 or equation 2 to solve for a. So I'm going to substitute this into equation 1. So in this case, r is 2, so we have 2 to the power 4 is equal to 45. 2 to the power 4 is 16, so 16a is equal to 45. A is equal to 45 over 16. Okay, so in this case, a is 45 over 16. R is 8, so our general equation here is 45 over 16 times 8 to the power n minus 1. Now, what you want to do is you want to find the 20th term. So if you want to find the 20th term, you plug in t of 20 is equal to 45 over 16 times 8 to the power 20 minus 1 is 19. You can leave your answer like this because this is a very large number basically.